Hello, grade 9s. Today we are going to start talking about circles. Now we all know what a circle looks like, but let's give it an official definition so that we're all starting off in the same place. So a circle is a closed shape made up of all points that are the same distance from a fixed point called the center. So if we come up with any point, any single point we want, in this case in my drawing it's called A, and I measure out this distance and draw a point. And I measure out that exact same distance in all directions. And I create all of these additional points all the way along the same distance away from that original center point, and I eventually connect them. I am going to create that circle. Now, circles are actually named based off of their center point. And so how we name them is we draw a circle with that center point inside, and then we name whatever that point is. So this circle on the right is named circle A. But if I drew a new circle and labeled that center point with a different letter, like T, then I'd have circle T as my notation. So circles are named based off of their center. Now, the cool thing about circles is that when I start mixing the ideas of circles and line segments and angles together, we get all of these really cool properties, all these really cool new terminology pieces. And we are going to start identifying some of the ways that lines and line segments relate specifically to circles. So the first one we have is a secant. And I can see a secant right here. Now this secant is a line that intersects the circle at 2 points. So I can see this line here. It goes on forever in both directions. I can see that because there are arrowheads. But when I see that line, I can see that it goes through the circle exactly twice. So there's 2 points in which that happens. Next, we have a chord. Now, a chord is this guy over here, and a chord is specifically a line segment, so it does not go on forever. It specifically has endpoints, and those endpoints exist on the circle. So I have an endpoint, and those endpoints exist on the circle. If I'm looking back to secant, if I had only a segment of that line, so I crossed out the parts where it goes on forever, and it stopped such that the endpoints were on the circle, I would also have a chord. So kind of neat, new definition there. A diameter is actually a type of chord. It's unique because it also passes through the center of the circle. So a diameter is a chord. It does, in fact, exist as a line segment with endpoints on the circle itself. But this type of chord passes right through the center. All right, next we have radius. And we all kind of know what the radius is. But the radius is half of the diameter. It connects the center of the circle to the edge of the circle, and that can be in any direction. So that purple line I've just drawn is the radius. This pink line I've just drawn, line segment I've drawn is the radius. This light purple line segment I've drawn is also the radius. Now, officially, I can say that the radius, which I denote with a lowercase r, is equal to the diameter divided by 2, or I can say r is equal to half times the diameter. Both give me the same final answer. All right, next is a tangent. Now, a tangent can be a line. It could be a line segment. It could be a ray, in which it only has an arrow on one side. But it's any sort of straight line segment, etc., that touches the outside of the circle exactly once. So a secant goes through twice. A tangent only touches that outside once. And that point in which it touches is called the point of tangency. Okay, there is an example of a circle below. This is circle C. And we want to identify each of the following things. Take a moment, see if you can identify all of the parts that it's asking of you. Pause the video, go. Welcome back. Okay, so given circle C, we're going to try and identify some of these things. So a chord is a line segment with endpoints on the circle. I have the option of AB. I also have the option of DE. Both of these are technically chords. So AB, or I said DE. Both of those are chords. A radius. In this diagram, I have the option of line segment DC or line segment CE. Again, the order in which you write these line segments or these letters does not actually matter. So if you wrote CD instead, super great for you. All right, moving on. A secant. Remember, a secant is a line that intersects the circle twice. So I'm looking at this guy over here. It is a line HJ. And my line notation requires I have that double-sided arrow at the top. Next, the point of tangency. Well, I do need to identify the tangent. So here is my tangent. It is a line that touches the circle, the outside exactly once. So I'm going to go ahead and actually do the tangent first, which I have is GF as that line. You could also denote it GK, KF. It's also fine. Both work. Now, if I'm skipping back to the point of tangency, the point of tangency is just the letter capital K. The center is point C, and the diameter, well, that's that special chord that we talked about at the beginning. Now that special chord is line segment DE. All right, so lots of new notation, lots of new things to remember, but once we kind of start putting the pictures together with the names or the descriptions, once we have that in our mind, it's really easy to identify. So it just takes a little bit of practice. Okay, now that was a lot of terminology, but we're not done. It was kind of just lines and line segments. We need to start talking about angles in a circle. Now we're going to introduce two different types of angles in a circle today. One of them is an inscribed angle. An inscribed angle is formed by two chords that have one common endpoint. Its vertex, which exists on the circle. Now when I take a look at this, so I have a chord here, I have chord TR, and I have chord DR. Now that chord does not have to be a diameter. Of course, in this image it is, but that is more than okay. But the idea is that those chords need to meet somewhere in order to form that angle. In this case, they meet at point R. They have the common endpoint of R. They form an angle, and that angle is an inscribed angle. Next, we have a central angle. It's a type of angle formed by two radii. Radii is really just the plural of radius. So when I take a look at this, instead of being formed by two chords, I'm formed by two radii. So I have one radius here, SP, and another radius here, BP. And of course, if I'm formed by two radii, I have to have that center of the circle as that common vertex, that point in where those two radii meet. Because every single radii in a circle will always touch that center point. That is called a central angle. Okay. Next, we have arcs. An arc is the distance, before we talk about an arc, I just want to talk about the distance around the circle. So we kind of already talked about angles, and we know we have acute, right, obtuse, straight, reflex, full rotation, and a full rotation angle is 360 degrees because a full rotation angle makes one full circle. So when we talk about the distance around the circle, that distance is 360 degrees. It's formed by one full rotation angle. Now, an arc is a part or segment of the circumference. So kind of like a line segment is a chunk of a line, an arc is a segment or a chunk of that circumference. So if the circumference is the total distance around, and we know that total distance is 360 degrees, an arc is just a chunk of that circumference. So part of that 360 degree total. Now, we typically define arcs by the endpoints. Now, that arc can be created by the endpoints when I have an inscribed angle. It can be created when I have the endpoints of a central angle. And any angle can touch the circumference at different points to create an arc. So typically we'll use that phrasing of an angle intercepts an arc. Now, notation-wise, we use the endpoints of that arc, but on top of it, we draw a curved shape so that it looks like the arc. So if I'm talking about this arc here, the arc that is intercepted by both the inscribed and central angle in this picture, we can call it arc BC or arc CB. The order of those endpoints doesn't matter, but I'm using those endpoints with a curved marking on top. Now, please be intentional that the marking looks curved, because if I do this, that looks more like a line segment from C to B, right? So I want to make sure that that intentional curved marking is shown at the top, so I know for a fact we are talking about an arc and not a line segment. Now, there are different types of arcs. There is a minor arc, and a minor arc is an arc that is less than half of the circle. So if a full circle is 360 degrees, then half of a circle is 180. And when I talk about less than half, I'm talking about anywhere between 0 and 180 degrees. So if my arc measures 107 degrees, it's a minor arc. 2 degrees, it's a minor arc. 179.999 degrees, it's a minor arc. So any arc that measures less than half the circle is considered a minor arc. Now, a minor arc is denoted, like as we said before, with those 2 letters with the curved marking on top. And those 2 letters come from the endpoints. Okay, so this minor arc here that's pictured in blue, which I'm now coloring in purple or shading in purple or writing over in purple, is denoted by the 2 endpoints with the curved marking on top. Okay, a semicircle is an arc that is exactly half of the circle. It measures exactly 180 degrees. Now, when we talk about that angle that intercepts that arc, this angle would have to be formed by 2 radii, but those 2 radii really come together to form a diameter, right? Because I'm at exactly 180 degrees going straight across. Think of this as a straight angle, creating that arc that's exactly 100 degrees, creating that semicircle. Now, when we talk about this semicircle, here it's pictured in green and I'm highlighting it in yellow, that arc. But please note that when I have a diameter that intercepts my arc here, I technically create 2 semicircles. Now, when we take a look at naming my arcs, how do I know if I'm talking about the yellow arc that I've just highlighted or the pink arc that I've just highlighted? I can't just say one's a minor arc, that's not true. And I can't just say, oh, it's the semicircle. Well, they're both semicircles, okay? So when we talk about notation for this one in yellow, I'd still use the endpoints, but I'd actually throw in some point in the middle so that I know which way I'm going. So I'm going from E, then hitting up H, and then continuing on to G as my endpoint. And if I'm talking about this pink semicircle, I can say it's E, J, G as the arc. And then it tells me that I go from point E to point J to point G. The reason that center letter is important is it because it helps distinguish and provide clarity of which direction I am going, which semicircle I'm referencing. Which kind of brings me to a major arc. Now we can probably imagine if a minor is less than half, semicircle is exactly half, then the major arc has to be more than half of the circle, which means it's between 180 and 360. Can't be 180 exactly because that's a semicircle, but it's somewhere in between there. Okay, now when we talk about a major arc, the reason major arc cannot be exactly 360, well, technically an arc is a part of the circumference, right? It's a portion of, whereas like the circumference is the whole thing. So an arc being a part, we don't typically refer to an arc when it's 360. We just say it's the whole circumference. It's that whole circle. Now, when we talk about major arc, anytime an angle, like this one here, angle BAC, has intercepted my circumference to create these arcs, there's technically two arcs it creates. It creates this minor arc that I can see, the small sized arc that exists between the two endpoints B and C, but it also creates this major arc that's still between the two endpoints. It's just going in the opposite direction. Now, kind of like when we were talking about a semicircle, we were saying, hey, we need to have that center letter in the name of my semicircle arc so that I know which direction I'm going. Well, to help distinguish between minor arcs and major arcs are always going to be just the two endpoints with the curve on top, because that's the assumed shortest distance between those two endpoints. When we talk about a major arc, the notation we use is the two endpoints, but we always put a middle point there. So when I'm taking a look at this one, I've started at B, I'm traveling, oh, hey, look at this, I hit at point D, and then I continue on to the last endpoint C. Now, something kind of interesting or something kind of important to note is that it doesn't actually matter how many labeled points exist here. So if I have E, I have point, F, point G, I don't have to put all of the middle points in between. I am just using the two endpoints, and to denote that it's a major arc, I'm choosing one point that's in the middle. So in this particular diagram, now that I've added those additional points along my circle and I've labeled them, arc BDC and arc BEC technically refer to the exact same arc. Okay? So I'm just using 3 letters to denote the major arc, because if it's only 2, it's assumed we're talking about a minor arc. Now that we know what arcs are, and we know the types of arcs that exist and how to denote them, we can also talk about calculations with arcs. Now, just to throw it out there, when we're talking about the measure of something, a measure of an arc, a measure of an angle, a measure of anything at all, typically we throw the lowercase m in front of it to represent the measure of something. So if I put the measure of angle ABC, I'm talking about the size, the degrees associated with angle ABC. If I'm talking about here, measure of an arc, so I have the measure of, in this case, this must be a minor arc because it is the distance between A and B along the circumference, but I only have 2 letters, so it must refer to a minor arc. And I could also tell it's a minor arc because it's less than 180 degrees. It's between 0 and 180. But this is how I can refer to the measure of. So typically we don't say like arc AB is equal to 50 degrees. We talk about the size or the measure of arc AB being equal to 50 degrees. So that M is just some notation that we'll see. It happens with arcs, it happens with angles. We'll just see it throughout the unit. But the reason that I want to talk about it now is because we're going to be talking about the measure of certain arcs. Now, first and foremost, all minor arcs and their corresponding major arcs, if they have the same endpoints, they will always sum to 360 degrees. So the measure of the minor arc and the major arc that are between the same points will sum to 360 degrees. So we have this example off to the right. So I have this minor arc here. So I say the measure of minor arc AB. And I also have the major arc that's associated with those exact same endpoints. So I can say the measure of the major arc. So I'm going from A, and I'm going the other way around. In the major arc, I have to add one extra point along the route. So I have arc ADB, and that's this pink guy over here. When I know they have the exact same endpoints, and I know that because A, I can see it, but I can look at those letters in which the arc starts and ends with, right? Because the endpoints are always apparent in the name. So I started at A and I ended at B, and again, the order doesn't matter, but I see an A and B at the end of both of those names. I know that those two measures will create the full circumference, which means that distance that it adds up to will be exactly 360. So this is what I note. I know that the measure of the minor arc plus the measure of the major arc will equal 360 degrees. Now what's kind of cool about that is if I know one of those two things, the measure of, in this case, I know the measure of the minor arc is 50 degrees, I can find out what the measure of the major arc is, right? Because I could substitute in the values that I know. I know that 50 degrees is the minor arc, 360 degrees, well, that's part of my equation that I've built here. And I could use my equation solving skills to solve for the measure of the major arc. Okay, that's one thing I can do. The second thing I can do is that when I'm taking a look at arcs and the corresponding central angle. So I have an arc that I'm talking about. Specifically, in this case, I'm going to be talking about the measure of a minor arc. And when I'm talking about the central angle that intercepts it, so in this case, I have angle ACB that intercepts to create that minor arc. The measure of that arc is equal to the measure of the corresponding central angle. I'm going to throw in the word minor here. But the measure of that minor arc is equal to the measure of its corresponding central angle. So if I know that arc is 50 degrees, I could substitute that in, and I can find the measure of that angle. So 50 degree central angle will have a 50 degree corresponding minor arc. Okay. Whew, that was a lot of content, but we have a couple of examples just to finish it off, just to make sure we can start practicing with that different notation and putting it to practice here. So I want you to pause the video and try the next two examples as much as you can on your own, and then play the video once you're ready to look at it together. Go. And welcome back. Okay, so a central angle I want to identify in this picture here. Remember, a central angle is formed by two radii. So I'm looking for two radii that come together to form an angle, and I can see this one here that I've highlighted in yellow. I can refer to that as angle SOP. T, but you're also welcome to refer to that as angle TOS. As long as that vertex O is in the middle, both names are acceptable. Next, I want to talk about the minor arc intercepted by the central angle. So I'm still talking about that central angle, SOT or TOS, but now I'm talking about the minor arc that exists between them. Remember, minor arcs are always going to be less than half the circle, less than 180 degrees, and it's denoted by the two endpoints, S and T, with that curved marking on top. Next, we have an inscribed angle. An inscribed angle is formed by two chords that have a common endpoint. So RQ and PQ are both chords, and they have that common endpoint of Q, which is now their vertex. I can call that angle RQP or angle PQR. As long as Q is in the middle, that is more than acceptable. Last but not least, we're talking now about the major arc intercepted by the inscribed angle. So I have that inscribed angle, angle RQP, but I'm not talking about the minor arc. I'm talking about the major arc, the arc that measures more than half of the circle. Now, when we talk about that major arc, we're using the two endpoints in the name, R and P, but we're using one point somewhere along that route. I'm going to use Q because that's what we use to define that inscribed angle anyways. So we're kind of already there. And I'm drawing that curved marking. If I used major arc RSP or RTP, that would also be more than acceptable. And again, the order can swap. I can say PQR or PSR or PTR. As long as R and P are on the end points of that name, and there is a single point somewhere in the middle that is along that route, that is an acceptable name. All right, last example. Now, before I talk about the last example or I'm solving for X, I just want to talk about what I have here. Now, I can see I have a central angle. I can see that's a central angle because it's formed by two radii. And those radii will always form a central angle because they'll always meet anyways, so they're always going to form that central angle. I can also see I have a minor arc here. Now, when I think about this, there's actually some stuff that I know, a property that I know that relates minor arcs and central angles. And what that property is the measure of the central angle will equal to the minor arc that it intercepts. Now you might be asking, Ms. T, why are you writing this down in words? Because I see that word explain in the question, right? Explain implies to use words. So I need to know why I'm able to do what I'm about to do. Now I just said the measure of the central angle, which is the measure of my central angle QRP or PRQ, both are cool, will equal the measure of the minor arc it intercepts. Measure of QP with that curved mark. And I can go ahead and substitute the values I know. Well, I know angle QRP, the measure of it is 60 degrees. And I know the measure of that minor arc is 3x plus 15 degrees. And now I can use my skills, my problem-solving skills from my solving equations unit to solve for x. Notice that I'm always going ahead and I am writing that degree sign with every single angle that I draw or write, as long as it's not connected to the letter or variable x, or whatever variable I'm using. The reason why I'm not writing that variable with x is because, not the variable, the unit with x, is because we assume x encompasses that unit. So I have 15 degrees is equal to x, and that's not in proper form here. We know that we should be writing our variable as equal to instead of the other way around. Okay, be warned that in this unit there's going to be a lot of examples where we explain our reasoning. And that explanation has to be clear and has to be coherent. And yes, that's more writing than we normally have, but that's one of the big skills in this unit, is to be able to explain why we are able to do things. We are not just doing things because that's what our teacher told us. We are not just doing things because we're blindly copying things down. We are always having that reasoning to back it up. So we make a move, we can explain why we're doing it. All right. Lots of terminology today, lots of new words, lots of new skills. But that's it for 6.4. Have a wonderful rest of your day. Bye.